issues about how the structure of the dark matter halos that I've been describing to you affects our chances of detecting the dark matter directly, either through an experiment on the Earth or by detecting its distribution in our own galaxy or in other galaxies through non-gravitational processes. So I told you last time quite a lot about the density profiles of dark matter halos, and there are two other aspects which I pointed out, which are generic, which is the non-spherical shapes and the large amounts of substructure. So let me first say a little about the non-spherical shapes. So these are a couple of examples of two dark matter halos. This one represents a galaxy group, this an individual galaxy, so this is a few times 10 to the 13 solar masses, a few times 10 to the 12 solar masses. And what's been done to make these plots is to try and construct equidensity surfaces inside the dark matter halo. So what they did is they went to each dark matter particle in their simulation. They looked at the density of other dark matter particles around it and assigned a local density to each dark matter particle. So as you'll see a bit later, when you do this, most of the densities are in some kind of smooth distribution, and then you find lumps, which are the substructures. So they excluded all the lumps and then looked for particles whose local density was about the same to try and localize equal density surfaces. So these are what these plots are. So this is three projections of all the particles whose density is close to 100 times the mean. These are the three projections of all the particles whose density is close to 2,500 times the mean, so a factor of 25. And there should be another 0 there. This is another factor of 25 higher. So this is actually 62,500. So obviously, as you go to higher densities, you only see the center, and you see these look ellipsoidal, so they project to ellipses. So to a good approximation, it seems these surfaces are ellipsoids, not so good as you can see for the outside one here. And so then, if you fit them to an ellipsoid, you can plot the best fits. And so what you see here is they're quite elongated. You can see the axial directions change. So this one is elongated up and down in the middle regions and on a diagonal in the outer regions. This one lines up at all radii, but it's much more elongated in the center than at the edge. This one's round in the middle and gets more elongated outwards. This one is horizontal in the middle and on 90 degrees. So you can see the axial ratios change as a function of radius, and their orientation tends to change. So if you now plot up the typical axial ratios to ask how far are they from spherical, this is just measurements for individual objects. So you can see that this one is flat. This is the longest axis divided by the shortest, so the shortest axis divided by the longest axis as a function of density. So this is low densities very far out. This is moving towards the center. The highest densities are very close in. And you can see as you move inwards, there's a tendency for most of them for this axial ratio to get smaller. So if you average, you get this. So you can see in the outer regions, the typical value, the average value of this ratio is about 65%. And in the center, it's less than a half. So in the middle, so first of all, you see as you go towards the center, on average, the shapes become more extreme, which you could see in the pictures. And in the inner regions, the elongation is typically, on average, more than 2 to 1. So it's not a small effect. And then this is the intermediate axis divided by the longest axis. And so you can see here, it's indeed intermediate. So they're not oblate or prolate, they're in between. So that's the typical results you get for the shapes. If you take different halos, just make a histogram, how many are very prolate, how many are nearly round, this is what you get. If you look at the left-hand side here, these are the axial ratios just histogrammed. The different histograms are actually different masses, and there's a slight shift, but it's fairly small. But the main point you can see, and these are different redshifts where they took the data. So you can see there's a shift here with redshift as well, where they've plotted this. And the axial ratios have a wide spread, but this is the shortest over the longest. There are tails all the way down to 0.2. so extremely elongated things. So there's a wide variety of shapes, and they're not spherical. Now I move on to the substructures. That's all I wanted to say about shapes. So we can ask, can we get convergent results for the number of small lumps inside of big lumps? This is more numerically demanding, because if you run a large simulation, you have a very large number of particles to represent the main halo, but still only a relatively small number of particles for the smaller lumps. So the question is, how well do the results converge? So this is for the Aquarius set of 5 halo simulations of the same object, with resolution varying by a factor of 2,000 from this one to this one. And then this is just the number of counts, a number of small objects inside. So you put a big spherical shell around what you consider to be the boundary of the halo. In this case, it's about 400 kiloparsecs from the center for something that looked like the Milky Way. And you just count the number of small objects inside that as a function of their mass. So this is the mass of the small object, and the mass of the main halo is 10 to the 12, so it's off the edge here. And so as a function of the mass of the small object, this is the number you get. So it's just like a histogram. And so what you see is that if you take the lowest resolution, you can only count down to this mass limit, because then you just don't have enough particles in the small objects to be able to see them any longer. So you get this curve stopping here. If you go to about this object, we've increased the resolution by a factor of 1,000. We can now count down to 1,000 times smaller mass. So you go 3 orders of magnitude further down this mass distribution. But what you can see is, except possibly for the very last point, they all lie on top of each other. So inside the range which is resolved, results are converged. Now it's not quite as good as it looks here. This looks very good because if you look, the 10 orders of magnitude plotted vertically. So if you derive, and this is very close to m to the minus 2. So if you multiply by m squared to flatten out this trend, now that's the bottom plot. There's now only 1 order of magnitude here. You can actually see the deviations better. And you can see, as you get to the lowest masses at each resolution, it tends to drop below the count. So that's the effect of the limited numerical resolution. And you need to get a factor of 5 or so above the lowest point plotted here before the results are really converged. The other thing you can see in this plot is that this curve is gradually going downwards towards low masses. So this means that this slope is slightly shallower than m to the minus 2. It's about m to the minus 1.9. This power law which is put through here is m to the minus 1.9. Now to get the total mass in these objects, you have to multiply the number by the mass and integrate. And if this was exactly minus 2, the result would be logarithmic divergent, which means that each decade in substructure mass will give the same contribution to the total mass. It's going down gradually. So what this means is, for the distribution in the simulation, each decade in mass as you go to smaller and smaller subhalos contributes slightly less to the total mass. But it's very weak. And so there's still some debate in the community about how definitely you can say this is less than minus 2. Okay, but I showed you we can do better than this in a convergence test, because we can actually identify the same small lump in the different simulations. So you can take the small lumps at the different resolution and then ask, are their properties the same in 2 simulations run with different numbers of particles? And that's the test that's been done here. So what's shown here, for example, is a function of the characteristic velocity assigned to a particular lump. So you can imagine that if there was a galaxy inside this dark matter lump, it's the typical velocity the stars would have. So as you go to smaller and smaller lumps, the velocities get smaller. So the smallest objects are over here on the left, the biggest objects on the right. And this characteristic velocity for the Milky Way itself, for the main halo, will be 200 kilometers a second, way over here somewhere. So now you take the small lumps, you find the characteristic velocity in the highest resolution simulation. That's the one 2400 here, one that's plotted here. And you take the next highest resolution, and you see how well they agree. And that's what's plotted here. So this is agreement to 10%, is within plus or minus 0.1, within 20% plus or minus 0.2. So you can see all the way down to about a few kilometers a second for the characteristic velocity, the agreement's better than 10%. You can measure a characteristic size. You can do the same thing. And the different curves, now, so this is the median agreement for the second one in the series, for the third one in the series, for the fourth one in the series, and so on. That's what the colored curves are. And the dots are just the actual values for the individual objects for these two. And this is how well the characteristic sizes agree. So you can see for the second highest one, it agrees with the highest one to within 10% down to here somewhere, which is a couple of hundred parsecs. It's a very small size. Right? Remember, we're 8 kiloparsecs from the center of the Milky Way. So this means for the biggest simulation, if you extrapolate this trend to how good the biggest simulation is, then we think it gives convergent results, meaning within 10% in these quantities, down to characteristic velocities of only 1.5 kilometers a second. So that's much smaller than the characteristic velocity of stars seen in any known galaxy. Even the smallest galaxies have characteristic velocities of 5 or 6 kilometers a second. And for sizes, down to 165 kiloparsecs. Distance from the point mass. And it's again, it's a spherically symmetric system, so it's just a two-dimensional phase space. So if you're very far away, the velocity is negative because it's still falling in, but it hasn't got even through one orbit yet. As you come in, the dark matter particles here, you get to this point, that's the particle which is just falling through the center for the first time. When it goes through, it comes out with a positive velocity on the other side. Then these are particles which have already been through the center. This is the one that's been through the center once, and it's just turning around for the second time, so it's here. Then you go through, goes through the center a second time, comes out here, and so on. So these series of oscillations, when you average over the whole distribution, means that at any given time, this is what the phase space distribution looks like. And you can see it's occupying a one-dimensional subset of the full two-dimensional phase space. So this is a spherically symmetric problem, so we have a two-dimensional phase space, only one-dimensional subspace is occupied, and it has this wrapped structure. So now let's ask, what's the density distribution look like? So this is the phase space density distribution. We have to project out the velocities to ask what the density distribution is, which is then projecting down this velocity axis. So if you project down the velocity axis, this is the density against radius. And you get this interesting structure. So there's an average profile fall-off, which is about r to the minus 2. But superposed on it, there are spikes that correspond to each turnaround. And these are geometric caustics, just like light caustics. So everywhere you have a turnaround, the particles stay at about the same radius for an extended period of time, and so this projects into this uniform caustic structure. So these are the caustics which form from folding of sheets. It's like catastrophe theory. If you now ask how does mass, you integrate up this density profile to get mass as a function of radius, you see the caustics are there, but in the mass profile you can barely see them. You can see the first couple, and then it looks smooth. So although the caustics are there, there's not much mass in them. Okay, now ask how will this affect the annihilation radiation? So the annihilation radiation as the particles go along depends on the local density of other particles. So as a particle goes around this spiral, it's going up in parts of this density profile. You can ask, what is the local density of particles? And you can integrate the annihilation rate. And you can ask, what happens when I go through a caustic? When the particle goes through this part of the trajectory, goes through here. So you can integrate up the local annihilation rate, you get an infinite result. Although there's negligible mass here, in this idealized problem, there's logarithmically divergent annihilation radiation. So this led to the idea the annihilation radiation could be dominated by emission from the caustics. So therefore, although you can't see it in the mass profile, or barely, maybe it has a strong effect on the annihilation. So this is why this was interesting. So what are the consequences of the Boltzmann equation? So we start with a three-dimensional sheet. It will stay three-dimensional at all times. The evolution will distort it and stretch it, but it doesn't tear it. So this means since the three-dimensional sheet fills space initially, it will always fill space. So that means there's some cold dark matter everywhere. There's no empty space. At every point you have to have at least one sheet, but most points you have more. So for example, here there's one sheet, here there's 3, here there's 5, here there's 7, and so on. In typical nonlinear objects, there are actually many sheets at every point, and these are what people call the streams. And what you saw when I showed you the velocity distributions is near the sun, there are so many streams you can't see them in the simulation. You don't see any particular preferred velocities. So the stretching, which reduces the density of the sheet, has to reduce its velocity dispersion because the phase space density is the spatial density divided by a velocity dispersion cubed. So if the spatial density goes down, but the phase space density stays the same, that means the velocity dispersions have to go down. So as these sheets get stretched by the evolution, the internal velocity dispersion gets smaller and smaller. The individual sheets get colder. But what happens at a caustic is the local density goes to infinity. So then the opposite happens, the velocity dispersions must get large as well in order to maintain the phase space distribution. And that's what regularizes the caustics. So as you approach a caustic, the velocity dispersions go up, they spread the particles out, and so you don't get the logarithmic divergence. So it's actually, even though velocity dispersions are small, they are what regularizes the behavior at the caustics and means that you don't, in fact, get an infinite result. So you have to calculate this in detail. So it is possible to do this, and I don't have any time to tell you about it. So let me just skip through all this part to the conclusions at the end. Let's start here somewhere. So the conclusions you get, what I didn't tell you about, which is how to calculate this, is to actually follow the geodesic deviation equation, as in general relativity, along every orbit, because that tells you what the local phase space density is doing, and you can actually identify the caustics directly without even looking at neighboring particles. So when you do this, you find this works, and you find well inside a cold dark matter halo, you predict very large numbers of streams at any point when you look at the full three-dimensional evolution, at least 100,000 or so at the sun's position. And that's why the velocity distribution in the simulation looks smooth at the sun's position, because there's just so many sheets crossing. So that's why we get the quasi-Gaussian signal. And as it turns out, when you do a fully three-dimensional evolution, the stretching is much larger than in the simple one-dimensional case that I showed you. And this makes the caustics weaker. So in practice, although this is all very neat, it looks as though there's negligible boosting of the signal. So once you take this stretching into account and the regularization due to the velocity dispersions, it seems they're not, in fact, significant. So the final thing was to say these are lots of things about the dark matter distribution which people have discussed in the literature at great length, and all of which are untrue, based on what I said. So they all tell you that the dark matter near the sun is mostly in small objects. They'll pick out Earth mass. This isn't true. I showed you the first object which formed is often much larger than that, and then it gets tidally disrupted. In fact, the extrapolation is that a negligible fraction of the mass near the sun is in small objects. They tell you that the streams made by this structure will mean the velocity distribution is clumpy, and this will make it much harder to interpret the momentum distributions. It's not true. There are so many streams that in fact it's to max well into a very good approximation. So this is to try and convince you can do tests to see how well these kind of numerical simulations are doing. So now we can take our 6 different halos and ask, if you count the substructures, do they agree with each other? How much scatter is there between one object and another? You know, if you only do one simulation at high resolution, you're not quite sure how well this should agree with the Milky Way because you only have one realization. So here we have 6. So here are the 6 different realizations. And this is the total number of objects down to some characteristic velocity plotted against that characteristic velocity. So 1 over here is 200 kilometers a second. This would be 20 kilometers a second. This would be 2 kilometers a second. And so what you see is this noise at the massive end, because it's such a small number of objects, it's essentially counting noise. Once you get down to very small objects, so you can see for the biggest simulation we count 300,000 little objects inside the big one. That's where this thing flattens off at the resolution limit. For the second level here, which we're showing for most of them, we're leveling off at about 40,000 small objects inside the big one. But you can see in this regime, where there are plenty of objects, there's no counting noise, they actually agree with a scatter of only 20%. So there isn't that much variation from one object to another. There is, however, variations between one simulation group and another. So we're not the only people doing these kinds of simulations. So these are the results for our set of 6. This is the result for the Via Lactea simulation, which Dima and Maddow and friends published a couple of years ago. And you can see it's clearly in disagreement by a significant amount with ours. And the disagreement is much larger than the scatter between our results. So there's clearly something to understand here. And then more recently, just last year, they published an updated version of this simulation with higher resolution, Via Lactea 2. That's the dotted line. So now you can see the dotted line is much closer to our results, but still outside the scatter. So at least between the different groups here, there are clearly some numerical issues. So they actually identified a problem with their initial conditions in Via Lactea 1. So the current hypothesis is the very big difference for the first simulation here was a problem they had in setting up their initial conditions, which they corrected for the second one. So now after they've corrected that, the differences here still looks bigger than noise, but it's not really big enough to worry about. So here are some properties of the distribution of the small objects inside the big objects. So let's start at the one at the top. This is asking how are the small objects distributed in radius inside the big object? How many are there near the middle as compared to further out? So what's plotted here is the number of small objects normalized to have an average of 1 over the whole region of the halo, and the nominal boundary we're taking here is here at 400 kiloparsecs. So the number density of small objects is a function of radius inside the big object. So you can see that as you go towards the center, the density of the small objects increases, but only rather slowly. So here at 10 kiloparsecs, it's only about 20 times higher than it is at the edge. So you can see there are 5 different colored curves here. The cyan one, which only goes down to about here, is the small objects with between 10 to the 9 and 10 to the 10 solar masses. So that's about between 1,000th and 100th of the mass of the main object. The purple is 1 order of magnitude lower in mass. The blue is another order of magnitude lower in mass. The green is yet another order of magnitude lower in mass. And the red is objects between 10 to the 5 solar masses and 10 to the 6 solar masses. So that's more than 1,000,000 times less massive than the small object. And you can see a kind of surprising result that when you plot up their distribution in radius, they all look the same. So it looks as though the radial distribution of the small objects is independent of their mass. All mass subhalos are similarly distributed. Now, then the next thing you can do is you compare this distribution in radius with the distribution of the total mass in radius. That's just the mass density profile that I showed you last time. That's rising much more steeply. So if you normalize here, the total mass would go up like this and hit the ceiling. So you can now go to each radius and ask at each radius what fraction of the mass is in the small objects that we can actually resolve. And so if you go out to the edge here, this nominal radius at 400 kiloparsecs, you can see the total fraction of the mass in small objects is about 30%, just to our resolution limit locally. But as you go in, the density of the total dark matter increases rapidly, while the density of the small objects only increases relatively slowly. So what happens is this mass fraction plunges. By the time you get to the radius of the sun, only 1,000th of the mass is in the resolved objects. So, where we're going to put our experiment to detect the dark matter, of course, is on the Earth. So that's here. So in the part of the galaxy that those experiments are probing, the fraction of the mass in the dark matter lumps that are resolved by this simulation is only about 1 part in 1,000. So almost all of it's smooth. And then the 6 colored curves here are just the 6 different simulations. So you can see again, there's not that much scatter between the different realizations, and the thick red curve here is just their average. Okay, well, we can only count in the simulation down to the limit of our resolution. We need to extrapolate all the way down to the smallest mass halos that can form, which we think might be an Earth mass. We saw how the number was increasing as you decreased the mass of the subhalos. So now we can try and extrapolate that. And it's a big extrapolation. We have to extrapolate from 10 to the 5 solar masses to 10 to the minus 6. So that's 11 orders of magnitude. So this is the plot. This is the lower limit you count to. Here's 1 Earth mass. Here's the limit of our best resolution simulation. So these are the 11 orders of magnitude. And this now is the fraction of the mass in the small objects in the system as a whole. So out to this 400 kiloparsecs. And here we're already at 20%. So now if I take this 0.9 power law and extrapolate all the way down, it goes to here. It's convergent, so really we don't get much extra. If I take the logarithmic divergent case which didn't look consistent with our numerical data, but maybe it's just in bounds, goes up to here, we'd have about 50% of the mass in the little objects. But that's because I'm counting all the way out to the edge. If I count just to 100 kiloparsecs, so that's only 4 times smaller, because of this flattening, we're way down. So here, now, we've only got 1% of the entire system, and we extrapolate, still only 1%, or 2% if I take this logarithmic divergence. So even out to the edge of the visible galaxy, the most distant stars we can measure about 100 kiloparsecs from the center, it looks like there's a maximum of 2% of the mass in any kind of substructure. And if I made the same curve for the solar distance, I get 1,000th of the mass. So, yeah.
Could you repeat that a little bit? So that's counting all the objects to that radius in the
This top curve is counting them all to this nominal outer radius.
Right.
And that extrapolates with the parallel I had. If you take the parallel I fitted to about, where are we? Well, that's the extrapolation is here, to just under 20%. And if I extrapolate logarithmically, to about 40%. But now I've done the same thing, limiting not at 400 kiloparsecs, but at 100 kiloparsecs. And that's this curve. And if I did the same thing, limiting at 10 kiloparsecs, it would be a lot noisier, but it would be down here, it would asymptote around 10 to the minus 3 of the mass. So because the power law is so shallow, even though there are 11 orders of magnitude, it doesn't gain you much. One final point before I start discussing detectability issues. Here's our biggest simulation. I put it on the side to be able to plot it here. So this is what it looks like. There are not enough pixels in the screen here to do it resolution, to do it justice. Here are 6 subhalos. So now we plot the subhalos. So we put a sphere around each of these and plot the particles separately. This one is A, here it is. B is this one, C, and so on. And what you see is that this subhalo, let's look at A, you plot it up, it has its own subhalos. So you have another level of the hierarchy. When you look at each of these, you can have there are 6 plotted here, so the last one is F. You can see they all have their own subhalos. So let's look at F, which is this one. It's down here, it has its own subhalos. So this one, let's take this subhalo, it's actually, you can blow it up, it's a binary, and so you can see the sub-subhalos have their subhalos. So let's take this one, blow it up, it's got its own subhalos. There are 3 here. So you can see, when you have enough resolution, you start seeing substructures of substructures. And so in this particular simulation, you can find 4 levels. So this is the case. So in the last level, there are 3 individual objects, here, here, and here in this one, which is then part of a binary, which is then this binary inside this one, which is this one. So you start seeing the hierarchical structure. So the conclusions from this of the substructure, there's lots of it, but it's primarily out near the edge, not where the sun is. The radial distribution of the subhalos seems to be almost independent of mass, and that sounds simple, but it's not. There are all sorts of effects which seem to counterbalance each other to give this result. The subhalo populations scale almost with the mass of the host, so if you go to a much bigger object and you just plot the picture, it looks the same. So everything scales up in the same way. That's what you saw that already in the introductory slide I had, which showed a Milky Way halo and a cluster halo. The subhalo distribution does, at least in our simulations, appear to converge as you go to smaller and smaller masses, but it's converging very slowly. Maybe it could still it's still possible it's logarithmically divergent, but I think it's sort of outside our current data. But even with this divergence, in the inner part of the halo, the substructures still only can contain a small part of the mass.
These are for present-day halos.
Yes.
Do you carry out for other epochs the analysis of substructure?
Well, you can. We haven't done this in detail, but it looks of the limited range you can do it. None of these results change. I mean, they change quantitatively slightly, but there are no big changes. But we can't go to very high redshift. But at very high redshift, I told you yesterday, there are no objects. That's once you go past redshift 13, most of the mass is diffuse. Okay, so let me come to issues of detection. So we would really like to have some way, except gravity, to detect this stuff, to prove to ourselves that it really is cold dark matter. I sometimes get the impression that everybody just accepts this, to the point that Eric said yesterday that dark matter was the idea only came up in the 1980s because that was when the current cold dark matter paradigm was established, and so this was in the back of his mind when he said this. But
particular fitting form that Jim Peebles had.
Fine. But I think, it is symptomatic that this paradigm has become sufficiently well established in people's minds that lots of young people basically assume this is, the paradigm, and it's only slightly strange people or perverse people who are out there trying to prove something that's different. Having started earlier, my point of view is until we actually find the particle, I'm not going to be convinced. So if we're going to try and find the particle, how are we going to find it? So there are a couple of kinds of detections. One is basically the equivalent of a laboratory experiment where you put a large bolometer, a crystal, and a cryogenic system down a mine shaft, and you try and detect collisions of the dark matter particles with the atoms inside your crystal, the bolometer. This is what's called direct detection because you're actually detecting the recoil energy when the particle bounces off the atom. So then you have to be, and that's sensitive to the momentum of the particle. So you have to know what the structure is on the scale of your detector. And that's a big sapphire crystal this far across. You need to know what the distribution of the dark matter is on scales of 1 meter. Our simulations give you the distribution on 100 parsecs. So there's quite a lot of extrapolation. Okay? Another way to detect it is that the particles, particularly, for example, if the light is supersymmetric particle, then they do have self-interactions, and in particular, the light is supersymmetric particles probably has a Majorana mass, which means it can, if two of them meet, there's a finite probability for annihilation into a whole slew of particles, including in the decay chain photons. So you get annihilation radiation. It's weak. It's not because this is predicted to be a suppressed process, but it should be there. And if we're lucky, it could be there at a level we could detect. And you'd expect to see it in gamma rays. So, for example, the Fermi, it's now called, formerly known as glass satellite, which has been operating now since early last year, has a reasonable chance, has a chance that it will detect this gamma ray annihilation directly. So we would have an image of the dark matter distribution. So how does that scale? Well, it's a collision process. The two particles have to meet to annihilate. So the annihilation rate in a unit volume depends on the annihilation cross-section, on the square of the density, because it's a two-particle process. So the total emission from some volume depends on this integral. So this is basically particle physics parameters that come from your supersymmetric model. And this is the astrophysics that tells you how the dark matter is distributed. What scale do we need to know the distribution on? You need to know the distribution around, on average, around an individual particle on the scale of the annihilation cross-section. So that's even smaller scales. So we have to be sure that what we see on the scales that we're simulating can somehow be extrapolated down to these scales and give you a correct answer. So these are unique predictions which are far below the scales that we can simulate. So without a good theoretical extrapolation, you could not be confident. Without a good theoretical understanding, you could not be confident of these extrapolations. So the issues for the various experiments, so for the lab experiments, the direct detection experiments, we need to know what's the expected cold dark matter distribution in space and also in velocity, because we need to know the momentum distribution with which the particles are hitting the detector on the scale of the apparatus. It's actually, you can think of, obviously, the apparatus is on the Earth, which is moving around the sun, which is moving through the galaxy. So you actually need the distribution on a line as the apparatus carves through space. For the indirect detection issues, you need to know how clumpy the distribution is. Because if you take something which is smooth on the large scales, and then you say on small scales it's broken up into little clumps, then the mean density over large scales is lower than the density inside the clumps. And because the annihilation radiation depends on the density around each individual particle, if you clump things, the annihilation signal goes up. So in order to predict the annihilation signal, we need to understand the small scale clumping of the dark matter all the way down to the smallest scales. And this is relevant for questions like, where should you look? For example, we see that dark matter is clumped in these small substructures. You can ask, are they dense enough that their signal could, for example, outweigh the signal from the diffuse matter? You can ask whether you can get dense structures which are actually not bound. And this is possible. They're so-called caustics. I may get to talk about that, depending how far I get. And something which I won't get to talk about, which is also an interesting issue, is you can ask, what do you expect at the center of the galaxy? We know there's a black hole there. The black hole affects the distribution of the material around it, and in particular, it will affect the distribution of the dark matter. And as the black hole formed, it will have pulled the dark matter around it. And so you predict there should be a cusp of dark matter distribution around the black hole. And we don't know exactly how to calculate this cusp. But if you do a naive calculation, you find you can get a divergent gamma ray flux from the cusp around the black hole. So there's a need to do this calculation better, because we know, in fact, there isn't a very strong gamma ray source at the galactic center. Is this the limit on the dark matter? Well, that depends on your ability to calculate what you should see. And that I certainly won't get to. So let's ask the detectability issue for the underground detectors. So the question is, at the position of the sun inside the Milky Way galaxy, how smooth is the dark matter distribution? So we can't go all the way down to the scales that are relevant, that I was arguing, but we can at least take our highest resolution simulation and look over the scales which are resolved by that simulation. So what's been done here is to take our biggest simulation with about 1 billion particles inside the Milky Way's halo, 1 billion simulation particles, go to each simulation particle and estimate a local density by counting the particles directly around that particle. So for each particle in the simulation, we have an estimate of local density. Then we look in the middle, between 6 and 10 kiloparsecs from the center, and we look at all the particles in this region, and they all have a local density. And we say, well, how well can we fit this with an ellipsoid? So we fit these individual particle densities to a model, which is a power law in radius, stratified on concentric ellipsoids, all the same shape, and we just fit by adjusting the power law parameter and the shape and the orientation of the ellipsoid, and see how well you can do and get a best fit. And then what's plotted here, this is the density at each particle divided by what's the mean here is the fit, is this model fit. So this should really say model, I guess, rather than mean. And you get histogram, which of course peaks around 1, and you get this distribution. Notice the scale here. This is 1. This is 10 to the minus 8. So this is the histogram. So it's peaked strongly at the mean, as it should be, because we fitted to it. And then we look at the width. So you can see there are two parts. There's this thing which looks like a parabola, and there's this tail of high densities. So this tail of high densities, you can see, cuts in about 10 to the minus 4, 4 orders of magnitude down from the peak, and it looks like a power law. These are the particles which are inside the substructures. The substructures are denser. So if you integrate the total amount of mass in here, you get a bit less than 1 part in 1,000, which is the number I gave you before. Those are the little lumps. This is the part that's not in lumps. Why does it look like a parabola? Well, it turns out this is just the noise in our density estimation. We estimated the density by sitting on a particle and counting how many particles there are around it. So there's a kind of Poisson noise when you do this counting. So if you take a perfectly uniform distribution of particles, a Poisson distribution, and do the same density estimate, what you get is this dashed histogram. So you can see the width here is entirely due just to the noise in the way we estimated the densities. Now it turns out that the measured distribution from the simulation, there are so many particles in here, about 100 million, that you can actually see the difference in width between the simulated result and what you get for a perfect uniform distribution. You can measure the scatter from the difference in variance. And what you find is the RMS scatter about the smooth model is only 4%. So you ask, how well is it fit by an ellipsoid? It's amazing. You can fit a simple ellipsoidal model with a power law stratified on concentric similar ellipsoids over this whole region, and it fits to within 4%. So what this tells you is that almost all the mass at the distance of the Sun is very well approximated, at least to the resolution we see here, by a simple smooth model. So that's good news for the experimenters. You know, they make a simple fit to the mass distribution of the galaxy. The number they get for the distribution near the Sun should be what they will see in their experiment. Because the chance of being out here in this tail, where we happen to be sitting inside a lump, is down by 10 to the 4. So you'd be very unlucky to be sitting in a dark matter lump. So therefore, the spatial distribution is smooth. That's one piece of good news. What about the velocity distribution? Because we care about the momentum. So here you go to a small region. You put down inside the simulation a box, 2 kiloparsecs on a side, at the Sun's distance from the center. And you just make histograms of the velocities in 3 directions, in the 3 different directions. So if you look at the velocity distribution, it actually has one direction where the velocities are slightly larger than the other directions. So it's what's called a velocity ellipsoid. So you take the principal axes of this distribution, and then just make histograms. And the actual histograms for a typical box are in red, and the best fitting Gaussians are the dashed black lines. And you can see the histograms are perfectly smooth. And the velocities range from over plus or minus 300 kilometers a second. And this is obviously the direction with larger velocities. These are the directions with slightly smaller velocities. So you don't see any preference for a large number of particles at a single velocity. This will be a so-called stream. If there was a trail of particles from some particular lump which had just passed through this region, you get lots of particles which all had the same velocity because they all came from the same orbit. You don't see that, typically. So the velocity distributions are very smooth. So that's also very good news. It means if you make a simple model for the dynamics of your dark matter halo distribution, that'll predict, say, these Gaussians. This should give you a very good idea of what the momentum distribution is. So from the experimenter's point of view, that's also good news. So you'd think that's all there is, everything's smooth, but it's not quite true. So here's something which was a bit surprising. Let's plot the energy distribution of all the particles inside a box. Now I've actually plotted lots of different boxes on top of each other here. That's the different symbols. And what you see is it's not so smooth. This is actually the equivalent of the phase space density, but the number of densities, basically you can think of this as the distribution of particles as a function of their energy. So for each particle now we're just using the amplitude of the velocity. But you don't see a smooth distribution, you see clear bumps. And this is an order of magnitude, so the amplitude here is tens of percent. And here, at the low energies, there are quite large features. So even though the individual velocity histograms were smooth and didn't show features, if you plot up the distribution of v squared of the energy, you do see features. Now there's some interesting things about these features. If you take a box on one side of the galaxy and a box on the other side of the galaxy and plot up their velocity distributions, you get the bumps in the same place. So that's why all these different boxes are all over the galaxy. So they repeat from place to place. If you look at the simulation 1 gigayear later, remember the orbital times in this region are about 100 million years. So they have all the particles do 10 orbits in a gigayear. You come back a gigayear later, you make this plot, the bumps are still in the same place. So they're stable structures over gigayear timescales. If you take our simulation where you have the same initial conditions and look at different resolution, so we can take the different examples, you again get the bumps in the same place. But if you take our 6 different halos, which are different realizations, they all have bumps, but the bumps are in different places. So this is a stable feature of each individual object, which changes from object to object. And it turns out that what we're actually seeing is the fossil structures of the assembly history. Because, for example, say there's a bump at this point. You can see this is slightly higher, about 20% above the smooth curve, or here. You find the reason there are more particles with this energy is because sometime long back in the history, something fell in and was disrupted, and it put all its particles on some particular range of energies in energy space. And then once the particles are on stable orbits, they just stay there maintaining their energy, and that lasts forever. So this bump means that in this particular object, something that fell in contributed lots of particles in this energy range and not so many in this energy range. So it turns out these features are fossils of the assembly process. So this means if we actually do detect the dark matter, you wait a few years, the experimental sensitivity will increase dramatically. You'll actually be able to make this histogram. Once you've made this histogram, you'll actually be able to read off from the local dark matter distribution the assembly history of the Milky Way. Okay, so you take the statistics, the numbers I showed you, you can, if you want to make them dramatic, you can say that with more than 99% confidence, the sun lies in the region where the dark matter density differs from the smooth value you get by fitting a smooth model by less than 20%. So that's good enough. The local velocity distribution of dark matter particles is similar to a Gaussian with no measurable lumpiness due to streams. But the energy distribution of the dark matter particles has broad features which tell us about its assembly history. I should have had my 40-minute warning, shouldn't I?
No.
Not yet? Oh, good. I thought I should. Really? Okay. Now let's look at the annihilation. So I didn't think I was going to get to caustics, but now let's do the annihilation radiation. So now let's take the highest resolution simulation, use the local estimates of density to estimate how much annihilation is coming from the region of every particle. So we now get, for each particle in the simulation, an estimate of the annihilation rate for that particle at the present time, and bin them up as a function of radius. And this is the curve. So this is 100 parsecs, 1 kiloparsec. The sun is around here at 8 kiloparsecs. The edge of the halo is out here. And this is a linear plot vertically. So you bin up the total annihilation radiation. This is our set of our convergence series. So you can see if you look at the two highest resolution simulations here, the red and the blue one, they differ significantly only within a few hundred parsecs of the center. So looked at this way, it's converged. And the other interesting thing is that most of the annihilation radiation is coming out 2 or 3 kiloparsecs from the center. So although most of the mass is out near the edge, because of this rho squared dependence, most of the annihilation radiation is coming from inside the sun. So this is true for the main halo. It doesn't look nearly as good if you take the little lumps because they're represented by a small number of particles. But as long as their density structure is self-similar, as long as we know the characteristic size and the characteristic mass, we can scale. And I showed you that turns out the scale, as long as they're self-similar, scales as the characteristic velocity to the fourth power divided by the characteristic size. And I showed you these seem to be converged down to quite small objects. So we can use this to try and predict what you get from the small structures rather than trying to evaluate it directly, and we'll get more precise results. So this is what you find. So here is radius. Here is mass contained in that radius. So if you just look at the mass, we're all normalizing out here, in this case, to 200 kiloparsecs. So let's normalize to 1 here. By the time you come to the sun, which is here somewhere, you've only got about 2 or 3%, no, about 4% of the mass inside the sun. You go in smaller. Sorry?
40%.
Okay. So that means, if you ask, if we normalize here, this is where the total mass is, how far in do you go to get half the mass? It's here. So the half mass radius is 100 kiloparsecs, slightly less, 90-something. Now let's do the same thing for the light from the annihilation radiation that I showed you. That's the red curve. If you ask, where's half the light? It's 2 kiloparsecs. So the distribution is completely different inside the halo of where the annihilation radiation is coming from and where the mass is. Now I told you, for each subhalo, we can estimate the luminosity from that subhalo from its characteristic mass and size by assuming it has a universal density shape. So then we can add up the annihilation radiation coming from the subhalos we can actually see. If you take all the subhalos with greater than 10 to the 8 solar masses, you get this curve. 10 to the 7 solar masses, you get this curve. 10 to the 6 solar masses, you get this curve. And 10 to the 5 solar masses, which is the limit of our best simulation in this series, you get this curve. So if you look at the thick green curve first, you can see that the thick green curve actually drops faster than the mass. And that's because of what I told you before. The subhalos are all out near the edge. There are very few of them near the middle. So where is most of the subhalo low luminosity coming from? It's coming from the place where most of the subhalos are, which is out at the edge. So that's why this green curve drops much faster than the blue curve, which is the mass, and much, much faster than the red curve, which is the annihilation radiation from the smooth part. Well, the trouble is, we've only got to 10 to the 5 solar masses. We need to go down to, say, Earth mass. So how do we do that? Well, it's a bit of a guess, but what you can notice is because the radial distribution of the substructures is independent of the mass, these curves are also independent of the mass limit you count down to. They're all the same shape, they just shift upwards as you include smaller and smaller objects. So what's more, as you go each power of 10, you can see they shift up by about the same amount. So you can just use that to extrapolate upwards the rest of the way. So that's where you end up if you extrapolate to Earth mass. So now you see that outside about 15 kiloparsecs, the small objects dominate. Inside 15 kiloparsecs, the smooth part dominates. So at the Sun, the smooth part is still dominating, but not by much. Okay. But notice also, this is rising very rapidly. And that's because of the fact that the radial distribution of the small objects doesn't vary much with radius. So although there's quite a lot of radiation here, we're sitting inside something which is an almost uniform distribution. So this light from all these small objects is distributed uniformly across the sky, whereas the light, or the annihilation radiation from the smooth part, is coming from 2 kiloparsecs. So that's all coming from the direction towards the galactic center. So the light from the subhalos is going to have a very different distribution on the sky than the light from the main component. So let me show you that directly. Here's the light distribution from the smooth component, just projected from some direction. So this is the whole sky. This is, you can see, it's very strongly concentrated towards the galactic center. Half of the light is within about 15 degrees, 13 degrees, I think it was. If you take the light from the subhalos that we can see, this is how it's distributed. They're all at large radius, so they're basically uniform around the sky, and the little lumps. And this is only going down to 10 to the 5 solar masses. Now, let's extrapolate all the way down to Earth mass. You don't see the individual lumps anymore. And what you see is the contrast from the center to the edge is less than a factor of 2, because they're all so far away. So it has a very different radial distribution. So you add them all together, what's the total prediction? It looks like this. So there are now about equal amounts in the part coming from the center, which is the smooth distribution, and all the substructures, which are the background haze. But now the question is, if we look at this, what should we look at? Do we look here, or do we look at these little lumps? Our argument when we wrote this paper is that if you're going to look at this distribution, surely you should look at this thing, not at this thing. But it's not really that simple. The reason it's not that, so let's ask if the background was, so we have to detect this against everything else, of course. Dark matter is not the only thing emitting gamma rays. So there are lots of other gamma ray sources which somehow we have to detect this against. So let's ask if the rest of everything else was uniform across the sky, then you can do a signal to noise calculation for what the signal to noise would be for detecting different kinds of things. So that's a calculation which you can do simply, so that's the one we did. So this is the signal to noise for detecting a small object in units of the signal to noise for detecting the main system from an optimal filter. And so what you see here as the red histogram is for the individual clumps, the signal to noise that's predicted. And you can see very few of them have a signal to noise predicted above 1% of that of the main clump, and you can see from the image Y, it's just there's much more emission coming from the main clump. So even though it's more spread out, with a uniform background, you still have much better signal to noise for seeing the large-scale component than for seeing the individual clumps. Interestingly, you can take the individual known satellites of the Milky Way, where we know how far away they are, we know how massive they are, and predict what their dark matter should give with our model, and that's this green histogram. You know, which one will be brightest? It turns out to be the Large Magellanic Cloud, because that's by far the most massive of the galaxy's satellites, and it's only 40 kiloparsecs away, which is actually relatively close. So but still below 1%. This is optimistic, unfortunately, because if you look at the backgrounds, this is what they really look like. So this is a model for the gamma ray background constructed based on the observations of EGRET, which was the best gamma ray all-sky survey before Fermi. And what you see is this structure on all sorts of scales all over the sky. And all of this is brighter than predicted for the annihilation radiation. So the detection problem is actually much more complicated than the simple case I sketched. So whether it's really easier to detect the diffuse emission depends on how well you can subtract this very inhomogeneous foreground, or whatever you want to call it, in the galactic center direction. So one hope for doing this is you hope that this foreground emission, which comes from other kinds of gamma ray emission processes, will have a very different spectrum from the annihilation radiation. Then you could use the spectral properties to separate them. So we'll have to see how Fermi actually does with this problem. But they are all extremely keen on it, so you can be sure they will do their best. And we may find out within the next year, I think, with the first results. So to make some conclusions about this, so that the Milky Way's, if you were looking at the Milky Way from far away, how much of the flux you see would come from the main galaxy and how much would come from the clumps. Well, it turns out you'd be completely dominated by the clumps. As seen by a distant observer, the total emission from all the small things is about 250 times the emission from the smooth part. But all the small things are hundreds of kiloparsecs away from us. They're in the outer galaxy, whereas the main component is only 8 kiloparsecs away. It's the galactic center. So the inverse square law gives a big boost to the smooth part because it's much closer to us. So when you take the sky map that I showed you, the flux from all the small objects is only 3 times the flux from the distant clumps. And what's more, the light from the center is concentrated in a relatively small range of angles on the sky, whereas the light from the clumps is an almost uniform background. So it'll be hard to distinguish from distant galaxies, for example. The luminosity from the subhalos is dominated by the small objects, and it's nearly uniform across the sky. And the contrast center to edge is actually a factor of 1.5. So if you go to the individual subhalos, then they have, for a simple model for the background, they have much lower signal to noise for detection from the main halo, and it will depend on the details of the background whether this holds up in the real case. And if you ask which of the known subhalos ought to have the highest signal to noise, a simple calculation will tell you it's the LMC, because the LMC has lots of stars, so maybe it has more gamma ray foreground as well. So this could be still have complicating factors. So I have no time to talk about caustics because I think the next lecture is supposed to start in 5 minutes. Is that right?
Well, you started 10 minutes later.
Well, so I think we should ask people what they want to do. If I talk about caustics, if I give you an even simplified overview, missing most of the details, it'll take at least 10 minutes. So, do you want that, or should we just have questions?
Can you do the black hole?
No, I can't do the black hole, because I don't have any slides on that. I'm happy to stop here. Sorry? Okay. All right. So to understand why you get caustics, you have to understand something more theoretical about the nature of the dark matter. So if we go back to the early universe before there was any structure and ask what was the expected distribution of the cold dark matter, so you can go to a period which is well after the dark matter decoupled from the other components of the universe, but long before structure formed, or they dominated the cosmic density, and you can predict what the distribution of dark matter particles should be in linear theory, and specify the distribution of dark matter particles as a function of their position, their velocity, and some time. So they're nearly uniform. So the spatial density is just the mean density of the dark matter at that time, with a linear perturbation from one place to another. And this is small. And then the velocity distribution is to a good approximation Gaussian. It depends, of course, exactly on what the cold dark matter particle is, with some characteristic dispersion. So what that means is the velocity scatters around some average velocity at each point by thermal velocity sigma. So rho is the mean density of this cold dark matter. This delta is a Gaussian random field with finite variance much less than 1 because we're in the early universe. The mean velocity here is just the mean velocity generated by the density fluctuations. So you can get that it's a gradient of a potential, and this potential, the Laplacian of the potential is related to the density fluctuation. This is just straight linear theory. And this is a thermal velocity, so you can take this to be a Gaussian, and the characteristic velocities are much less than the velocities of motion. This is what we mean by the matter being cold. Right? So this is the theoretical distribution. So if you look at this distribution, it means in the full six-dimensional phase space at a given time, the cold dark matter only occupies a thin three-dimensional sheet in this full six-dimensional phase space, except for this small width. So in the completely cold limit, sigma will go to 0. The distribution of the cold dark matter in the six-dimensional phase space would be just three-dimensional. And that's an approximation because of the finite thermal width. Now the evolution equation for a collisionless set of particles is the collisionless Boltzmann equation, which says following any orbit of any particle, the phase space density is conserved. So this means at any later time, under completely general evolution, the cold dark matter still only occupies a three-dimensional phase space, a three-dimensional subspace of phase space. But because of nonlinear evolution, the structure of this three-dimensional subspace becomes very complicated. So let me show you a simple example. There's a simple solution for the simplest possible case in a cold dark matter universe is you take an absolutely uniform Einstein de Sitter universe and you put a single point mass on top of it that perturbs the potential. So now the Einstein de Sitter universe, every particle was marginally bound. If you put an extra point mass in, they're all bound, but the further away you are from the point mass, the less bound they are. So if you take any particular, and of course it's still spherically symmetric. So you take some shell of particles, this is radius, this is time, these are just dimensionless variables, then it starts off expanding with the universe, so this is actually co-moving radius. Then because it's bound, because of the extra point mass, it falls in, goes to 0 radius, because it's collisionless, it comes out the other side, and then it just orbits around. So every shell follows a track with time which looks like this, and this radius is going down because I'm looking at an expanding coordinate system. In a fixed coordinate system, these oscillations would have a constant apocenter. So that's what a single shell does. So now if you look at all the different shells at a given time, then you get this. This is now the velocity in the radial direction, and this is the distance from the point mass. And it's again, it's a spherically symmetric system, so it's just a two-dimensional phase space. So if you're very far away, the velocity is negative because it's still falling in, but it hasn't got even through one orbit yet. As you come in, the dark matter particles here, you get to this point, that's the particle which is just falling through the center for the first time. When it goes through, it comes out with a positive velocity on the other side. Then these are particles which have already been through the center. This is the one that's been through the center once, and it's just turning around for the second time, so it's here. Then you go through, goes through the center a second time, comes out here, and so on. So these series of oscillations, when you average over the whole distribution, means that at any given time, this is what the phase space distribution looks like. And you can see it's occupying a one-dimensional subset of the full two-dimensional phase space. So this is a spherically symmetric problem, so we have a two-dimensional phase space. Only one-dimensional subspace is occupied, and it has this wrapped structure. So now let's ask what's the density distribution look like. So this is the phase space density distribution. We have to project out the velocities to ask what the density distribution is, which is then projecting down this velocity axis. So if you project down the velocity axis, this is the density against radius. And you get this interesting structure. So there's an average profile fall-off, which is about r to the minus 2, but superposed on it, there are spikes that correspond to each turnaround. And these are geometric caustics, just like the light caustics. So everywhere you have a turnaround, the particles stay at about the same radius for an extended period of time, and so this projects into this uniform caustic structure. So these are the caustics which form from folding of sheets. It's like catastrophe theory. If you now ask how does mass, you integrate up this density profile to get mass as a function of radius, you see the caustics are there, but in a mass profile you can barely see them. You can see the first couple, and then it looks smooth. So although the caustics are there, there's not much mass in them. Okay, now ask how will this affect the annihilation radiation? So So the annihilation radiation as the particles go along depends on the local density of other particles. So as a particle goes around this spiral, it's going up in parts of this density profile. You can ask, what is the local density of particles? And you can integrate the annihilation rate. And you can ask, what happens when I go through a caustic? When the particle goes through this part of the trajectory, goes through here. So you can integrate up the local annihilation rate, you get an infinite result. Although there's negligible mass here, in this idealized problem, there's logarithmically divergent annihilation radiation. So this led to the idea the annihilation radiation could be dominated by emission from the caustics. So therefore, although you can't see it in the mass profile, or barely, maybe it has a strong effect on the annihilation. So this is why this was interesting. So what are the consequences of the Boltzmann equation? So we start with a three-dimensional sheet. It will stay three-dimensional at all times. The evolution will distort it and stretch it, but it doesn't tear it. So this means since the three-dimensional sheet fills space initially, it will always fill space. So that means there's some cold dark matter everywhere. There's no empty space. At every point you have to have at least one sheet, but most points you have more. So for example, here there's one sheet, here there's 3, here there's 5, here there's 7, and so on. In typical nonlinear objects, there are actually many sheets at every point, and these are what people call the streams. And what you saw when I showed you the velocity distributions is near the sun, there are so many streams you can't see them in the simulation. You don't see any particular preferred velocities. So the stretching, which reduces the density of the sheet, has to reduce its velocity dispersion because the phase space density is the spatial density divided by a velocity dispersion cubed. So if the spatial density goes down, but the phase space density stays the same, that means the velocity dispersions have to go down. So as these sheets get stretched by the evolution, the internal velocity dispersion gets smaller and smaller. The individual sheets get colder. But what happens at a caustic is the local density goes to infinity. So then the opposite happens, the velocity dispersions must get large as well in order to maintain the phase space distribution. And that's what regularizes the caustics. So as you approach a caustic, the velocity dispersions go up, they spread the particles out, and so you don't get the logarithmic divergence. So it's actually, even though velocity dispersions are small, they are what regularizes the behavior at the caustics and means that you don't, in fact, get an infinite result. So you have to calculate this in detail. So it is possible to do this, and I don't have any time to tell you about it, so let me just skip through all this part so the conclusions at the end. Let's start here somewhere. So the conclusions you get are what I didn't tell you about, which is how to calculate this, is to actually follow the geodesic deviation equation, as in general relativity, along every orbit, because that tells you what the local phase space density is doing, and you can actually identify the caustics directly without even looking at neighboring particles. So when you do this, you find this works, and you find well inside a cold dark matter halo, you predict very large numbers of streams at any point. When you look at the full three-dimensional evolution, at least 100,000 or so at the sun's position, and that's why the velocity distribution in the simulation looks smooth at the sun's position, because there's just so many sheets crossing. So that's why we get the quasi-Gaussian signal. And as it turns out, when you do a fully three-dimensional evolution, the stretching is much larger than in the simple one-dimensional case that I showed you. This makes the caustics weaker. So in practice, although this is all very neat, it looks as though there's negligible boosting of the signal. So once you take this stretching into account and the regularization due to the velocity dispersions, it seems they're not